So I think I took the title of this session to be a provocation, and roughly something like this. There are many results in the literature where you see comparisons like the one which is shameless promotion from one of our papers, which is from weak lensing simulations. But there are many similar plots you see in different contexts where there's 2 points you can make. One is this power spectrum constraint on some parameters in red. Then there is some non-Gaussian statistic in green. Here it's peak counts and lensing maps. And then there's a neural network, which is here in blue. And then A, you can see that the power spectrum is the worst. If you involve non-Gaussian statistics, it's better. So that's good. But then you do some machine learning and you get an even more impressive constraint. And then the question of the posed in the title of this session was, does this, I think this is what was meant as a possibly killer for non-Gaussian statistics, because why bother with smaller error bars if you can get even better ones? I think I know the answer to the question unambiguously, which is that non-Gaussian statistics are not redundant, they're alive and well. And that's pretty much all the answers I know. So after that, I mostly have questions. So I listed a bunch of questions here, which I could go through, and then hopefully we can discuss them. So there's six questions here. The first one is, well, first of all, have the Gaussian statistics become redundant? At least if you want to do cosmological parameter estimations, I assume it depends on the type of data. So CMB is almost Gaussian, although we already heard from Colin that the non-Gaussian parts are important for depending on what you want to do. Of course, the large-scale structure, as we've seen, is very non-Gaussian on small scales and has potentially much more info, although we could discuss how much more and do we know that number. And what is the trade-off between getting this extra info with the non-Gaussian statistics versus the messiness of going to small scales? So has the question, and in fact there are approaches where people simply cut the power spectrum in the nonlinear regime and just try to stay safe and just use the power spectrum, in which case the power spectrum or Gaussian statistics are alive and well, but arguably they're not the best parameter estimates. Second, so I guess I was going to go through these, but people can jump in since it's written here. So I just have a few more questions about why the non-Gaussian statistics actually have not become redundant. Is this mostly because the alternatives to using them are too expensive computationally? Is it because it's just new and we're just starting to employ the machine learning tools? Or is it because the results are less robust to systematics? This has come up before today, that the systematics might hurt the very nonlinear machine learning results more than the traditional statistics. Or is it just a lack of trust in these methods because we can't interpret what the machines are doing? So fear of the unknown. That's the second question. Then I guess the third one would be, well, will we ever be 10 years from now in a place where it is actually true that people are just using these machine learning tools and you no longer really read papers where people discuss the bispectrum or peak counts for weak lensing? And will that ever happen? And if it does, then why would we get to that point? Is it just how good are our machine learning constraints? If it's 1,000,000 times better, then yeah, maybe you won't bother with the other ones, but it doesn't seem to be 1,000,000 times better. It seems to be a factor of few better. Or is it, actually I just wanted to discuss this in general terms, like why would we declare why would we stop using ever this traditional statistics? Yeah. So yeah, actually, yeah. Please jump in.
I mean, redundancy is kind of like a strong thing, right? I mean, why not do both and maybe, figure out how to compute covariances between them, or maybe make machine learning algorithms that are orthogonal and then have just, both of them at the same time. That could be one option.
Yeah, so I think you're saying non-Gaussian statistics are here forever.
I mean, we've invested a lot of time in them.
Anybody disagrees with that?
I mean, I guess non-Gaussian statistics covers a broad range of things, and some things, like, at least to me, when you start looking at measures of the topology and things like that, it's not clear to me that those are more easy to interpret than a convolutional neural network, or that they would be more robust. So there is some non-Gaussian statistics that aren't maybe robust or interpretable as well.
So I'm personally actually very interested in this question of is it actually, so there's a lot of sentiment that the machine learning results are unreliable because they might be more affected by systematics and less robust. So I would be curious what people think, whether that's true or not. Yeah, I think.
Yeah, I think
people can just shout, like, even.
Yeah, I think I have some comment on this. So forgive me if I sound too aggressive on these questions. So I think first we can reverse this problem and ask if the non-Gaussian statistic can do almost the same as training a neural net. Why we bother training a neural net instead of using the simple statistic? Secondly, I think some of the questions are real. So going back, this kind of a big philosophical problem of interpretation of machine learning. I think one difference of the machine learning results and the traditional mathematical results is that when we use a mathematical tool, there's a mathematical system, right, with provable properties behind it. So I think when we talk about interpretability, it's really about both the fact and the feeling that we kind of can use some mathematical solidity behind this tool to predict the behavior or to kind of have the feeling of the behavior of this thing. And on the other hand, usually machine learning, I mean, neural nets now is just using some particular validation in particular data. We still lack the mathematical understanding behind it. So I think usually it can be seen as a trust problem, but I think science is always just about trust, right? But the mathematical system really behind traditional statistics provide us, I mean, sometimes stronger belief of things. And another point I want to raise is that so for example, for CNN, the main advantage that it runs very quickly when after training. So it will be very advantageous if we have a situation we just need to train it on a small training set, and we need to apply it to a very large data set. But that seems to me not the case for cosmology, because usually like for LST or for HSC or for DES, we just have a particular set of cosmological data set. And if you do the CNN way, you need to train on this particular set. And after training, you're not going to apply the result massively to other data sets. So then we kind of lose this advantage of being quick. So instead, usually CNN is the slowest way to do parameter inference. Right. That's my view.
Yeah, any comments on this? I think I agree with you. There was an example on in weak lensing where the Ribley paper, where they apply the machine learning to the simulated maps, and then they were actually able to find a new statistic, which was delivered by the kernel, so which was discovered by looking at the kernels of the deep neural network, and it was just the shapes of basically the gradients of the peaks on the map. And then that statistic, you could throw away the network afterwards. So arguably is what you're saying. An example of what you're saying, where the network actually was useful, but just only to point us to a new statistic. But Chirag, you had a...
Do you mind using your seat mic, please?
Something. Yeah, if I can come up with like a infinite validation suite and I throw the neural network at through all of those and it passes through all of them and I can never tell, like it does not fail any of the checks that I can think of, then maybe I can still not interpret it, but I would probably trust it in that case. So they are not the same questions, I think. The problem is like, even if I cannot interpret it, one of the problems that we have right now is there is no validation suite. And I think people have discussed this in some other places that most of the work that is done right now is like I pick a set of simulations, I train it, and then I hold out some set from the same simulations, and then I show that things work on that. I think Camels is like one data set where they're actively trying not to do this, but even there you have only like two simulation suits, and we don't know if we like both of them are consistent with the data on some sense, but we know that both of them are not the same. So even there, you would not know if you can trust either of them blindly to predict to follow the to be the true model of the data generation that we have. So that I think goes into the trust problem regime, that like how do you essentially come up with a technique that that you can be able to trust it? Like how do you generate such a validation data set that whatever machine learning algorithm you have put on is able to get the correct answer? Like, do you just run it on different simulations with like different resolutions with different n-body or like hydro models? And at what point do you start to say that so just using an ML approach blindly on validation data set, or you can like put something in the network itself. So you start throwing in symmetries, you start to come up with invariant statistics that the ML can predict, which you'll learn. So I think that they are like interpretability and trust are these two different problems in that sense. And for trust, we have to think differently from that.
Comments on this? I guess one question I have, is this part worse than for some of the non-Gaussian statistics? Because arguably they also suffer from similar issues.
Yes, so I would say not necessarily. That's why I don't know if I'm voting which direction. Just more food for thought.
Yeah, I'm not sure we need to vote because I'm pretty sure the result
Yeah.
will be that everybody will think non-Gaussian statistics are great. So any more comments along these lines? Yeah, on the back.
Yeah, I think 0.6 is interesting in that there is in some sense a very large continuum between like, I mean, technically a CNN is a non-Gaussian statistic, right? It's just one that very difficult to describe. And there's this large continuum, and there's been mentions of, we can look at CNNs, try to extract statistics from them, or try to I don't know, use symbolic regression, extract kind of condensed theories from learned models, and so on. So I think it's not really necessarily like, oh, we just have this or we just have that, but rather there's a large continuum that we can kind of exploit. And in the end, if we want to kind of maybe have very ambitious analysis that combine all kinds of different sources of data, then at different scales, we might be tempted to use different things. So at very large scales, maybe even the linear Gaussian theory is good. At medium scales, maybe we have some strong non-Gaussian statistics that we trust and we have good analytical models for, and they're just faster. And maybe at very small scales, we resort to some CNNs or other learned statistics, and kind of combining all of them together, we create a model that is able to exploit kind of information at all scales.
Another comment on this on the back?
Comment on like applying this CNN technique in general. The problem I have, so I mostly work with CMB data analysis, and problem of trying to apply this kind of technique to data, aside for the technical issues, that I basically have not much intuition about when things go wrong, how to go about it. Let's say I'm looking at CMB power spectra and I see like strange feature, I have this kind of intuition about like at this scale, what might be happening here. So I try to look at the data and try to process it differently and apply like correct for it or some whatnot. But in terms of like CNN, once I have this model, trained it, apply the data, I get some result. And if that result doesn't make sense, it's kind of, I only have a limited, I guess, tool to try to mitigate that. So in terms of actually thinking about trying to apply this technique to the data, not simulation, I think that was my most challenging aspect for me, at least.
Actually, it would be useful for me myself to know. I think the list where these techniques were actually applied to data for cosmology inference is extremely short. But I would love to hear examples. So, I mean, have you encountered this in real life where you applied some neural network?
I mean,
other estimates in the CMB? Or is this a hypothetical? The example I know of in weak lensing, I know of exactly one application to actual data for the kids survey, and as far as I know, they didn't run into a particular difficulty in that case. So these fears did not seem to materialize. But if people should weigh in. Has there been other applications that I missed? Or
related comment. It's not. I don't know of another application, but I mean, one thing that I've learned from training neural networks is that it basically, when you start, you don't get it to work out of the box, but it actually requires a lot of experience with how you have to pre-process the data, what kind of data the models can work with, how to design your model, and I think that in a lot of times, as you get more trained, you have an easier time applying it to data that has like specifics. I've actually, so I guess the example I'm working on right now is BOSS spectra, which were noisy and had like masks in them, and I think with the previous knowledge, just the experience of knowing how to like deal with data and how to pre-process it, I think I could make it work really comparably quickly, but it still took me like 2 or 3 weeks of hyperparameter tuning and.
This is for data?
This is for spectroscopic data, not maps. That's just like experience that I can share.
Yeah, Chirag, one more comment.
I wanted to, like, just going back and following up on what Wenda said, is that we have a spectrum of non-Gaussian statistics that we can probably combine. That's also like what Vanessa said, that maybe we can use non-Gaussian plus machine learning methods and combine. And also someone raised a point, I think from here, Olivier raised the point in emulator talk, in Kate's talk, that maybe you can do linear power spectrum analysis on large scales and use emulator for short scales and then combine them in a hybrid fashion. So like that example essentially tells that like we kind of understand emulators and Gaussian processors much more than we understand CNNs, but even there we have no idea how to combine the approaches. And that's a good, that's a very important problem that we should probably solve. So I'm all for that. The other point that I wanted to raise was,
sorry, just to be clear, you're saying is how to combine.
I mean,
two different, let's say, constraints on parameters from two approaches.
I'm saying not only combining at the level of constraints, but like at the level of analysis, is what I'm saying. So basically like doing the whole covariance analysis the way you do, but going beyond that, if you're going beyond Gaussian statistics in that case. But the one thing that I think might be tricky in combining ML approaches with this, oh wow, that mic is loud, is that the way at least I understand it is that like when you combine it with these more interpretable non-Gaussian statistics, is that you are essentially just anchoring your ML framework. I'm not sure if that solves the problem of either trust or interpretability on the ML part. It just more serves to anchor that part to something that we know it's the truth. So it will not be completely biased, but and hopefully close to the truth, but that does not mean that I would write like, yeah, it does not make it any more interpretable, the ML part by itself, in my opinion. But if that's the case. So it's a different question and it's a different thing, but again, just pointing the difference between two things.
Yeah, so I think one thing people have talked about is to give the neural network not just the data, but also give the summary statistics simultaneously with the data. So I don't know if, and then see if it's like getting a boost for your network. So do people have examples of this that they want to share or in the room?
There was some paper by the Harvard people, Michelle and Tampa, who did this. They call like hybrid networks. And yeah, it's like, it trains much faster, right? You don't have to teach the network to compute the power spectrum. We know how to do that. So.
But did they get, did the leg up for the network actually improve the?
I think it trains much faster and
constraint from the network.
I think so. It trains faster, and then you are guaranteed that this information is already included. So you teach the network to extract information beyond the power spectrum. You put in the very last layer.
All right. So any more on this? So I think, well, for number 3, the answer is the non-Gaussian statistics will never become redundant. Or maybe.
I think this discussion might be a little bit premature in that, speaking mainly from spectroscopic large-scale structure analyses, like non-Gaussian statistics hasn't even been used for a full analysis that we trust, right? There's been like a bispectrum paper with Boss, but there's a lot of caveats with that. And people haven't really studied in detail systematic effects and all these things with non-Gaussian statistics. So it's hard to say they've become redundant when a lot of the machine learning applications, as promising as they seem, none of them have even done the level of the non-Gaussian statistics for studying all these effects that can affect analyses. But of course, if someone does all of the large body of work required to establish trust, in the method, then I would happily accept 1,000 times better constraints.
Yeah, I think it's a big psychological barrier when people start really applying to data, the machine learning stuff. But Vanessa, you have a...
Exactly, like also just chime in there, because so this criticism of, oh, I haven't seen this yet applied to data, I think it's actually a good thing. I think it means that we as a community are doing the right thing. Like, we should not apply it to data yet because we haven't quite, understood it and figured out all of the, we are still developing the methods. So I think that's actually good.
Yeah, go ahead.
So maybe I'll be a little bit controversial here. I don't know, but I'd like to hear from people who are more expert than me. Is like, do we even know how much more information there is to extract? Because on some of these, some of the claims where I see huge improvement from non-Gaussian statistics. Usually, I struggle to see like. Sometimes, for example, for some parameters, we know kind of all the information is in the linear power spectrum. So I'd like to kind of see comparison of like even neural nets or non-Gaussian statistics with sort of linearly evolved linear power spectrum or something like that. And we know, okay, not all of not for all parameters all the information is in that, but that could be a good benchmark. And it kind of information content in the initial conditions. I haven't seen much of how much can we even hope to extract. And that would make me, when you if you show me, okay, here's what information is in the initial condition, and here is how close, including this neural network or including just bispectrum and trispectrum, this is how close we get. While with nonlinear power spectrum, we only get so far. I don't know if people have comments on that.
I think that's a great question. I'd love to hear if people have opinions on this. But one comment, I think it's not, as far as I know, you could actually, so the initial so one approach to, so I think you're asking great question, which was kind of my parentheses on the top right, how much information is in small scales. And what you're saying is one benchmark is look at the initial power spectrum.
For example, but
I think you could actually even generate more information, right? Through the nonlinear evolution, you could make the field more sensitive to some parameter.
Absolutely, for some parameters, yes.
So even that is not a safe upper limit.
Information. That's why it can generalize, like how much information there is in the nonlinear field if we could observe it without systematics. That's kind of I haven't seen a good answer to that.
So Agnes, did you have a?
Yes. So I think I agree, and I think this question kind of depends on what we want to study. And for instance, I think that for like large scale structure like weak lensing, to constrain just the lambda CDM parameters, I don't think we would need to go to the non-Gaussian level. Maybe I'm wrong. But some things I want to say. So one thing is we are not at the limits of using the information from the Gaussian part alone to test gravity. So there is still a lot of work even in the Gaussian part. And it has been shown that adding the bispectrum, for instance, would really help modify gravity. And I think it would help also, I think some people have shown that like constraining massive neutrinos and stuff. So I think that's an additional layer of difficulties that I think it will be like really, for weak lensing at least, I think the non-Gaussian part would be very useful for non-standard physics. So you also need to like validate your methods in non-standard physics, which is additionally difficult.
As you say, neutrinos is a perfect example of this. It's like, okay, if you claim you have a non-Gaussian method that gets neutrinos 100 times better, intuitively, I would say I don't believe you, but, I don't have a good, I don't have a super, I don't have a mathematical proof, but, asking how much, what's the information content of, and I know Adrian had paper recently and others, right? But you know, what's the best? You know, let's say I have information of the field at this redshift or on you know, some redshift range up to some Kmax of, you know, some resolution of the experiment, and then, you know, what's, you know, the ultimate kind of neutrino information I can extract, and then I can you know, the constraints from non-Gaussian statistics like bispectrum and stuff, they are more meaningful to me in the sense that now we say, okay, bispectrum gets us 98% of the way there, or like, you know, bispectrum barely makes a dent, and I don't know what you know, what my prior is always most information on these things are power spectrum, and then bispectrum helps more, and then, you know, less and less. But, you know, again, I don't have a proof, and I don't know what, you know, what fraction are we capturing.
Yeah, so Simone, I mean, the paper of Adrian recently, I mean, is kind of a little bit in contradiction with the things that we have been doing, and I think we both agree that probably, in this case with machine learning, probably this is the best way to see exactly which one is better, right? So this is probably one of the few cases where I will trust more a CNN than other methods that we have. And regarding the information content, I think this is a super tricky thing. You know, from the things that I've been doing, I can tell you that you can go to K of 300, you can have a contamination by baryonic effects from string models, and there is still cosmological information there once you marginalize over baryonic effects at the level of a single galaxy. So it's not super clear to me.
Yeah, I mean, I would even be happy with like a toy model at the beginning. Okay, you know, it's like, let's say you have, you know, finite, you know, only up to certain K, or, you know, however, smoothing scale, you know, the smoothed sort of field, you know. Yeah.
Did you want to add something?
Yeah, I think, I mean, part of this can be answered through like empiricals by looking at simulations, right? So if you believe that simulation somehow has about the same amount of information, so, you know, okay, they're not exactly faithful to the true model, but, you know, maybe we add some information here, maybe we subtract information there. And if you believe that, you know, we're all kind of correctly doing the train test splitting, and we're not looking at the split testing set too much and so on, then looking at the simulation performance does give you an idea of how much content there is in there, right? It's a low bound on the amount of content we can get. So maybe part of answering this question will be on perhaps some simpler simulation models where it's more realistic to create larger Helder models. We can kind of create more Helder data and then just test some of these hypotheses, see what is the best, you know, the best we can recover these parameters, and then just measure that on test set and check that, you know, it gives you what you expect, or much better than you expect, or worse than you expect.
Okay, Vanessa.
The simplest, like, standard first step would be to have a common data set to apply this to, because right now there are a lot of papers out there, like just in weak lensing, for example, that, you know, give different contours. They all claim to be LSST like, but in the end they've trained on different data, have maybe made slightly different assumptions for noise and redshift distributions and so on. So it's kind of hard to compare them in the first place.
Actually, I think that's a great idea. And yeah, especially between papers, it's very hard sometimes to compare error bars. So one could make available a whole suite of simulations. People can do whatever they want, and then next publish some test cases, and people submit their answers. So
I see some people on Zoom, they have questions. So
I wanted to mention, maybe for this, Vanessa, just in time, sorry for the advertisement. So I'm about to release a lot of data for this. You know, in this campus we have, and there will be hundreds of thousands of maps from different fields like gas temperature, dark matter density, and, you know, I've been 6 months training this CNN. This is the most boring thing I have done in my life. But I'm gonna release, all the things so we can really compare with a benchmark. And people doing wavelets or whatever thing, we can really compare in this same framework. So I completely agree with you.
Yeah, this would be great. I think it has to be organized in a way that people catch on. It happened in other cases where it was spectacularly successful. The famous Santa Barbara cluster.
Can I just recommend it is blind, or part of it is blind. I mean, the part of it, like the blind to cosmological parameters, right? Otherwise, I don't know what we'll learn.
I mean, for my case, this is for cosmological parameters, but you also have some astrophysical parameters that you are supposed to marginalize.
Yeah, no, the astrophysical parameters if you want, but all I'm saying is that it's sort of easy to tune the model to agree with we want to show that these methods are unbiased, not just not only compare the error bars, I guess, right? So I mean, for example, I mean, for this analysis of like full shape, Oliver and others, before they applied it to data, they did with Mazahir, they did this blind challenge, and I thought that was very useful, and that's what kind of convinced me that they were doing, the proper thing, right?
But I think what we're saying would be 2 stages. First, share maps with their cosmological parameters, and then people do whatever they want, and then the second stage is blind.
Yeah, I mean, you can start with that, but you can, then you should have a blind component, and then you say if you claim you have tiny error bars, if you don't, then you end up with a huge bias, right? If it's actually, if it's not true that you have tiny error bars in practice, then you'll end up with a huge bias, and you'll see it in the blind. Yeah.
So in our case, Simone, we even have like 2 completely different simulations, this Illustris TNG and this Simba. So one thing that many of you are familiar is that usually you can train on Illustris TNG, things work perfectly there. When you apply your CNN to Simba, nothing works, like dramatically. You could have flipped a coin and it would have been more accurate than this. So in that sense, I think this will be perfect because, you can.
In which case you would have to, withhold one of the 2, so that the training only happens on one.
Yeah, exactly.
Yeah, I was just going to say, follow up on Simone's stuff. The simulations you're saying about the blind full-shape galaxy clustering ones, it's actually still an ongoing challenge. So there's a load of BOSS-like data sets, which the idea is anyone can use their favorite ML or PD perturbation theory model to predict the power spectrum, bispectrum, etc. And currently, I think 3 perturbation theory people have passed it. All of the ML attempts have so far failed, but it's still an ongoing challenge. It's quite a nice blind resource for that.
Do you have
sadly no neutrinos. Oh, it's Takahiro Nishimichi's website, I think. Just blind perturbation theory challenge, I think.
A really important thing to, if you actually want to do this, is to decide whether the test data is sort of similarly distributed or intermingled with the trained data, in which case you're doing an interpolation problem, or whether, let's say the whole data is a Latin hypercube, and then you give us trained data some orthant of it, like an octant of it, and then you supply as maybe validation data another octant, and then as test data one of the super disjoint octants, and then I think everything will collapse.
Yeah, no, but I took your suggestion, Vanessa, to be the simplest thing. Just here's your method, you can calibrate it, here's the data on which you can calibrate it, and we're not gonna have hard problems. Just the first step is from the middle of the training set, how the various methods do. if you pull a model from the middle of the training.
So, I mean, there's no reason why you can't do all of them. Like, so if you look at, so currently, for example, there's a challenge at NeurIPS for, it has nothing to do with cosmology, for catalyst prediction, so a chemistry problem. And chemistry also has this issue where, you know, the data you train on, which has some of the molecules have, might not be the same molecules as you're using to test, because, you know, they look different. So that's kind of extrapolation. And then you can just construct kind of different splits where, like, you have splits, this is the data you train on, it should be kind of, this split of data should be the same distribution, this split will be different in the reactant, and this split will be different in the catalyst, and this split will be different in both. And then you can construct a whole suite of splits and see how they work there. I think, you know, if as a community we want to organize something like that, you know, and send it either to a big ML conference or a big cosmology place where it attracts the, you know, attention and so on it deserves, these are kind of things that you can work out and look at essentially what similar communities have done for these kind of, you know, ML competitions where there's no restrictions on methods. The only thing is that matters is how well you do on data. We can look at what other communities have done recently and submit it as like kind of challenges to conferences and emulate something similar.
I think this is great. If this happens, it grows out of this discussion. That will be a big step forward. I think organization is a big challenge. So actually, I'm happy to keep talking about this. We only have a few minutes. Well, 4 minutes. I think we can skip this. This is just to compare the various statistics. I guess it's actually kind of what we were talking about. And maybe 4 and 6 together is just one question of well, it would be comparing the AI methods, neural networks, etc., with other techniques. Particularly, thing I find very interesting are these reconstruction methods, where you want to actually reconstruct the initial condition together with the cosmological parameters, or the scattering transform we just heard about. So I guess my controversial question was, which of these is likely to be the biggest breakthrough? I don't think we'll get a straight answer, but maybe something good in the last few minutes. People want to comment on this?
Yeah, so I would also advertise this kind of transform, although I think in many cases it's actually a proper way to go. But beyond that, I would also like to comment on some inspiration the kind of the non-Gaussian statistics can have on CNNs, because like the architecture we have in CNNs are mainly developed in computer vision, so they have their own goal and their tested features, which might not always apply to the astronomy data we have. So, for example, the spectra data set is not translation invariant. So whether CNN is the best architect to go for is still a question. And also I'll go back to the complexity argument I made before. So it seems still to me the physical fields we have is actually much more simple than what we have in the biological world. So then the problem is, do we really need so many layers in the convolutional neural net in order to train it? Because like from the structure of CNN, actually the depth is not only for levels of complexity, of nonlinearity, but also for scales. Kind of the reason we have like 8 layers is not because we need 8 layers of nonlinearity, but mostly just because we need to cover the largest scale, and because the kernel are small, so we need to do it gradually. So can we kind of design, given the simplicity of the field, can we kind of design a new structure which does not really require so many layers? Perhaps just 3 layers of complexity is enough, but it just kind of design something to be able to cover all scales within 3 layers. I think that might accelerate a lot the training of convolutional neural net, because kind of the experience from galaxy morphology we have is actually people use both ResNet, which have many layers, and AlexNet, which is much shallower. It turns out the performance are almost the same. So then I really always have a question, why bother use the very complicated structure and finally just get the same result?
That's actually a fair point. Our maps look, our data looks much simpler than most of the applications of these neural nets. I guess we could end on that note, but it's 5 o'clock. But why don't?
If we have, sorry, I don't know if we have a dedicated session to that or if there are going to be talks, but sort of, is there any feel for, I mean, this, to me, I mean, I'm not, really actively working on that, but really experts in the room. And so just reconstructing the initial conditions, why isn't that clearly the way to go? If it's not, what we should be doing instead is the question.
I can talk about it because I'm doing that, but I mean, for me, like field-based reconstruction is like much more than just replacing non-Gaussian statistics, because there I see like it's one of the most robust ways, and if you are getting information on the full field level, then that's the best you can do, right? Like if I can model every observed point, so that's probably the best you can do. But at the same time, it's like a high risk, high reward problem, and it's like a super optimistic scenario. It's like the eventual goal, finally. So if you ask me if it will replace non-Gaussian statistics, eventually, yes. What eventually means is different for different people, I think. But at the same time, the gains are probably there much more than just getting like constraints on 5 parameters of interest, because you get the full field. You can use it to robustly combine different observables in a forward modeling way, where you can put in all the systematics and stuff that Chang was talking about, that you can like simple systematics like fiber collision. You can forward model it all the way, but you cannot get the inference part of it. So you can make those kind of approaches like full tractable in this formalism. You can combine different observables. You can also use it for like denoising the data, like the way we were doing it for 21 centimeter, where I'm losing modes. So, and then you can use the initial conditions that you have generated for other supplementary analysis like galaxy formation and stuff. And Borg people have already been using that for some supplementary analysis with LIGO and other data. So that's why I said I think like field-based reconstruction is probably like the eventual goal to solve all the things at the same time. But then the question comes is like how tractable it is, and currently we have a long way to go, because we cannot even do the inference correctly for this thing. Like there have been recent works which kind of get some constraints on cosmological parameters, but the full pipeline is highly inefficient, and even then the forward model that is being used is only LPT on a small box. So, I mean, I can go on length about talking about the challenges, but in my opinion, that's the most correct way to go, but that's also like the most hardest way to go. So that's the long and short of it.
I think there'll be talks about this, I believe, later on. There'll be talks about reconstruction, I think.
I think so. I think Yen Li is giving a talk, but that's more on the technical aspects of thing.
We have one talk. Max.
Oh, Max is giving a talk. Sorry, forgot. Sorry, Max.
But we don't have I don't think we have a session for it. Yeah.
So I think we're kind of out of time by 8 minutes. So should we wrap up on this note? It will be interesting to see what actually happens.